All right. Well, actually, it's a tiny bit. No, it's 10:30 on the dot. All right. So here we are, online again for it looks like the second time this semester. So that's okay. These online sessions are fun because, obviously you don't have to travel or anything. But anyway, so here's what we're going to do today. Of course, we had the test the other day. And so now it's time to start chapter 11, which is our introduction to probability theory. And we're also being introduced to a very interesting branch of mathematics called combinatorics. Oh, really? Is there a problem with the sound? Let me just double check. Yeah, it always makes me wonder if I am somehow have turned something off that I shouldn't have. Is anyone else having an issue? Okay. Yeah, I don't know what that's all about. It doesn't seem to be on my end. Let's see. Yeah, whenever there's a problem, I mean, sometimes rebooting is all that you need. So I don't know what the issue is. But if other people can hear, I guess it's not coming from this side. Okay. All right. Well, anyway, in the meantime, yeah, that's just it. It's technology. What do you expect? It's always going to let us down. All right, good. So, all right, so we'll find out what the problem is. But anyway, so we're going to be looking at chapter 11, and just as an aside, the final exam is just based on these last two chapters, 11 and 12. So it is not comprehensive. You'll be happy to hear. So chapter 11 is our introduction to probability theory and counting techniques, which are part of a branch of mathematics called combinatorics, and we'll be starting with that. And it's kind of an interesting area. It's something you may have had some exposure to before, but if not, I think you'll find it to be pretty interesting. And it just so happens that this particular area of math, it's easy to find good videos for these concepts. I don't know why. Maybe it's just because it's more fun or whatever the reason is. I have several excellent videos that I would like to show you, and which I was going to show you anyway. It's just that online, maybe it's even a little bit more convenient. So we'll start with our discussion here of chapter 11. And then when we get to a certain point, then I can start showing you the videos. Some of them are pretty serious, and some of them are just fun. Okay, so there's a little of everything for us today. Okay, so first things first, what exactly are we doing in chapter 11? Well, this is probability theory, but we start with the fundamental counting principle, in which what we're trying to do here is explain how many different ways there are to arrange a collection of objects. Okay, now what exactly does that mean? Well, it turns out that what we're trying to do is take a group of numbers and see how many different ways we can arrange those same numbers. And so here's an example that I came up with. Imagine down the road when you're, like doing crazy well in your profession, and you find yourself owning 3 beautiful cars, and you have a 3-car garage at your mansion. And the question is, how many different ways can I park those 3 cars in my 3 garages? So I've drawn up a list here to show you how this can be done. Of course, I've abbreviated them. This one means I've parked the Infiniti in garage 1, the Lexus is in garage 2, and the Mercedes is in garage 3. And then here I've changed the order a little. I start with the Infiniti, but then I put the Mercedes in garage number 2 and the Lexus in garage number 3, and so on and so on. And when you see the list, this covers all the possibilities. And you can see there are 6 ways I can park the 3 cars. So each of these choices is referred to as an arrangement. Okay, that's the formal name of of when you take a group of objects like this and change their order. Each one of those is an arrangement. So that raises an interesting question. Now, you can see that all we had to do here was take the 3 cars and write out all the possible ways we can park the cars. But that could get very awkward if we have enough cars. Let's say we bought a fourth car, and built a fourth garage. Or what if we had 5 cars and 5 garages? How many different ways would there be to park the cars? Well, that could start to get very time consuming to figure out by simply writing them all down. So we hope that there exists some kind of formula or function we can use to help us figure this out directly. Well, it turns out that there is such a thing. There's a function, mathematical operator, I guess I should call it, which would enable us to do this directly and in a very quick and easy way. And so let me just show you what it's called. It is known as factorial. Okay, there is actually a button on your calculator. On the calculator, it's labeled X factorial. And we're going to use it in a few minutes. And it's a very simple function. And you'll be surprised by the results. Okay, but first, let me show you a couple more examples. Hold on one second. Okay. Yeah, so let's take a look at a few more examples, but the mathematical operator that we will be able to use to help us figure out how many arrangements there are is this factorial operator. Okay, so let's go back and take a few more looks at some more examples. So imagine now you've got, let's look at, let's go revisit this garage problem. Suppose that we now do get a fourth car. Okay, we get a Rolls and we build a fourth garage. Okay, so now we got 4 cars and 4 garages. How many different ways can we park the cars? Well, the way to think about it is that instead of listing them all, which we could certainly do, but it would take a long time, in the first garage, there are 4 different ways we can choose a car to park in that garage. Okay, so in other words, for the first garage, there's 4 cars. We can pick any one of them. But once we made that choice, when we get to the second garage, there's only 3 cars left. So there's only 3 different ways of parking a car in garage number 2. And when that choice has been made, when we get to garage 3, there's only 2 cars left. So there's only 2 ways that we can park the cars in garage number 3. And when we've made that choice, there's only 1 car left. So that means there's only 1 more choice. So what ends up happening is that the number of ways we can park the cars is actually just 4 times 3 times 2 times 1, which is 24. As you can see why we didn't want to write them all down, because that would have taken all day. So there are 24 different ways of parking the cars. In other words, there are 24 arrangements of the cars that we can produce. And in fact, if you want to try that strategy back here with this first example, you can see that we had the 3 garages. There would have been 3 ways to park the first car, 2 ways to park the second car, and 1 way to park the third car. So the number of ways of arranging these cars would have been 3 times 2 times 1, which is 6. Okay, so in other words, that you could have used instead of simply writing them out if you know that at the time. Okay, so in other words, there's 6 ways to park 3 cars, 24 ways to park 4 cars. And in every case, what we're essentially doing is simply multiplying the number of possibilities for each choice, and then we end up with a result like this. So what that implies is that if there had been a 5th car, then the number of choices would have been 5 times 4 times 3 times 2 times 1, which is 120. So the number starts getting very big in a hurry, okay? Because each time we have more possibilities and we're multiplying more numbers together. So now we're ready for this factorial operator. So going forward, whenever we need to know the number of ways of arranging n objects, we don't have to draw any pictures. We don't have to, write out a list. All we have to do is use this factorial operator. So on your calculator, and by the way factorial is defined, you'll notice it doesn't work for any negative values. It doesn't work for fractional values. It's only defined for the whole numbers, meaning 0, 1, 2, 3, etc. And so the way it works is that 0 factorial equals 1, 1 factorial equals 1. And then it gets interesting. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. And it goes on and on and on. And you can see that 4 factorial is 24. 5 factorial is 120. 6 factorial is 720. Now, why don't we get some practice here? Why don't you get out your phone calculator? And this will be so simple. What you're going to do is look in the bottom left-hand corner, and the key that you're looking for says x factorial. So the way it works in this calculator is you hit the number that you want. In fact, let me pencil this in here. On your calculator, you would type 4 factorial, and you don't have to do anything else. No equals, no parentheses, and it comes up with 24. So it's kind of convenient, but of course you have to know how it works. Oops. And then of course, to reproduce this one, you just type 5x factorial, and you should get 120. And then for this last one, you hit 6x factorial, and you'll get 720, which is correct. Okay. So it's there are some functions scattered throughout this calculator that do not require the equal sign. And this is one of them. But anyway, so give that a shot. Make sure you're getting all 3 of them. Now, in the next slide, I'm showing you 2 more examples where the numbers are starting to get quite large. For example, try 10 factorial, and you'll say, oh my God, is that even possible? Look at that. It's more than 3 million. And if you think that's big, try 30 factorial, and you might be shocked by what you see, because the number is so large that the calculator actually has to show it to you in scientific notation. In other words, if you look at the very, very end there, that little E32 tells me that this is actually 2.6525, et cetera, times 10 to the 32nd power. Oh my God, that's a big number. It's probably, that's in the order of the number of atoms in the entire universe, that kind of thing. But just be aware when you look at it, don't forget to look at the end, and just in case there's scientific notation there, and there is in this case, E32 again means you're multiplying that number by 10 to the 32nd power. Very good. All right. Well, now here's a quick silly example that I came up with on the spur of the moment. Suppose that there's this very hot new artist out there in the market, and what he specializes in is these paintings where it's a white canvas with one colored dot somewhere on that canvas, and he's all the rage right now, and his paintings are selling for millions of dollars. In galleries in the village, everybody has them. Okay, so you decide to buy 4 of these for your mansion with your 5 cars. All right, remember, this is the future when you're crazy rich. You got the 4, and you've got, let's say you've got space in one of your rooms for 4 paintings. All right. And so the question is, how many different ways can I hang my paintings? And so the answer to that question is 4 factorial, because these are all arrangements. We're hanging the 4 paintings possibly in different orders, and there's 4 of them. So you can try 2 different things. You can go through the steps that we had before, 4 times 3 times 2 times 1, or you can just recognize that that's simply equal to 4 factorial, which means that there are 24 different ways I can hang these paintings. All right. And let's say you've got posters hanging up on your wall in your room. You may want to know, how many different ways can I hang my posters? Well, let's say you have 5 posters. Then the number of ways of arranging those posters on the wall is 5 factorial, or 120. Beautiful. So hopefully everybody gets what we've done so far. Now, the factorial operator is useful in its own right, but it also is used as part of more complex formulas, as we'll see. So it forms a foundation for some more important concepts that we're about to look at. And one of those is something called permutations. Now, what's happening here with permutations is that we're not just taking a collection of objects and rearranging them. Instead, what we're doing is we're making choices. So for example, if you have, I don't know, let's say you go to a restaurant and you're looking at the appetizers and there are 10 and you want 2, you're very hungry, you want 2 appetizers. You're choosing 2 objects from a larger collection of 10. Now, what's important about permutations is that you're choosing objects from a larger collection, but the order of selection is important. Somehow the order in which you make your choices is important. And let's say, if I choose, let's say 1 followed by 2, it's a different choice than 2 followed by 1. So if that happens, then each choice that I make is called a permutation. Now, here's the question. How do I calculate the number of permutations that are possible when I pick a certain number of objects from a group? Well, it turns out there's a formula, but it involves the factorial operator that we just learned. So let's look at this example. Imagine that the students of SUNY Purchase decide to start up a math club. Now, I'm sure all of you would love to join it, but let's just say in this example, there's only 10 members. All right. Now, according to the rules of the school, we must have 3 officers, which are the president, the vice president, and the treasurer. And let's say I'm the faculty advisor for this club. And I discovered that while I mentioned to them they need to have these 3 officers, they do not want to volunteer for these positions. So instead, I have to randomly assign the jobs to them. So I'm going to give every person in that club a random number from 1 to 10. Okay, so they all get a number. And then I randomly choose 3 numbers. And let's say I come up with 3, and then 1, and then 7. Okay, so I'm randomly picking numbers. I come up with 3 followed by 1 followed by 7. And that means that student number 3 is the president, student number 1 is the vice president, and student number 7 is the treasurer. Now, here's the important detail. If I'd picked the same 3 numbers, but in a different order, for example, what if I picked 731 instead of 317? Although those are the same 3 numbers, which means the same 3 students, this time, student 7 is the president, student 3 is the vice president, and student 1 is the treasurer. That's not the same, is it? So these 2 choices are actually different from each other, in spite of being the same numbers. So because they are different from each other, that means that each of these choices is known as a permutation. Okay. Now, by the way, it's not an arrangement. That would require us to take all 10 students and just change the order. That's what we would mean by arrangements. Just take them all and line them up and change the order. This is different because we're only choosing some of the students in the class, and the order in which I do it matters. So therefore, each of these is a permutation. Now, here's the big question. How many different permutations are possible in this case? In other words, how many ways can I fill these positions? Now, it turns out that there's a formula to do this. And that's a good thing because this would have taken a long time otherwise. Imagine sitting there writing out all these possibilities. Well, it could have taken quite a while. So here's the formula that we'll be using. Now, NPR stands for number of permutations, and N is the number of objects that we are choosing from, and R is the number of objects that we're actually choosing. So in other words, in our case, N would be 10 because we're choosing from a collection of 10 students, and R is 3 because we need 3 of them to fill these positions. You can see all we have to do is calculate the ratio of 2 different factorials and we're done. Okay. So it isn't that difficult at all. So why don't we try this example? We're going to have N is 10, R is 3. So therefore, you'll plug in these numbers, 10 for n, 10 minus 3 down here. We have 10 factorial over 7 factorial. And you can see that the ratio of those two numbers is 720. So that seems like a lot, doesn't it? There's actually 720 ways that I could fill these positions. That's why I said you do not want to get involved with making up a list in a case like this. It was one thing when we had 3 cars in our garages, or maybe even 4, but this, no, here you do not want to write this out. All right. Oh, absolutely. Yes. Yes, this is one of the awkward things about being online. I can't tell if anyone's falling behind. I can't watch you, you know what I mean? So you have to let me know if I'm getting too far ahead. All right, let me know when you're ready. All caught up? Excellent, excellent. And then how about this slide? Is everyone caught up on this slide? Okay, good. Now let's try another example. More practice is always better. So here's a horse race. Now, what's happening here is that when you bet on a horse race, I don't know that much about this, but I do know that you're allowed to place a bet, in which you bet. You're basically betting on who will finish first, second, and third. Okay. Now, so for example, if in this case, there are 8 horses running and their numbers are from 1 to 8. If I place a bet on 1, 2, 3, that means I'm saying that I think that horse number 1 will come in first. Horse number 2 will come in second. Oh, okay. So if you get kicked out, this video will be made available on YouTube, so you can watch the parts that you missed. I know how frustrating that is. You notice how batteries always die at the worst possible moment. So if that happens, don't worry, you won't actually miss anything because you can watch the video. Okay. Anyway, so I'm betting that horse number 1 finishes first, horse number 2 finishes second, and horse number 3 finishes third. Over here on the right, I've got the same 3 numbers, but if you notice, this time I'm betting that horse number 2 wins, horse number 3 finishes second, and horse number 1 finishes third. Let me send back a message. Okay, so in other words, they're different. And that is all we need to know to determine that each of my choices here are permutations. Okay, so how many ways can I bet on this race? Well, given that there are 8 horses and I'm picking 3 of them, that means if I plug in the numbers into this formula, I'm going to have, I should jump ahead a little bit. Here it is. Let's keep this visible at all times. So I'm going to end up with 8 factorial over 8 minus 3 factorial . All right, so for today's challenge, why don't you go ahead and figure out what that's equal to? I'm writing it slowly to give you time to catch up. Now, so it's 336. What you can do is just put 8 factorial divided by 5 factorial equals. You only need one set of equals this time. Usually you need more than that, but here you just need the one because each individual factorial is being done without the equal sign. That's just how they set it up. So you end up with 336. Now, you're probably wondering right about now, if I choose objects from a collection in such a way that the order matters, I know that each choice is known as a permutation. But what if the order doesn't matter? What if I choose objects from a collection and the order does not matter? Like the example before with the appetizers on the menu. If I pick 2 out of the 10, does it matter what order I ask for them? No, absolutely not. You're still going to bring the same 2 appetizers to my table, no matter what order I ask for them in. When that happens, when the order does not matter, instead of permutations, they're now known as combinations. Okay, so the key here is that we're choosing objects from a collection in such a way that the order does not matter. Aha, so the order no longer matters. And of course, that means the formula will be different. Now, let me show you a fun example of this. Okay, here's a case where we're going to the mall. And guess where we're going? We're going to Haagen-Dazs. Okay, this is the Westchester Mall. They have a Haagen-Dazs there. And of course, they have loads of cool ice creams, but they also have toppings for those ice creams. I'm sure you know this from experience. So you go to the Haagen-Dazs, and let's say that today you're having a special promotion. You can have any 2 toppings you want for $1. So if you buy an ice cream, you can have any 2 toppings for just $1. Now, it turns out that they have 5 available. All right. Now, when you think about it, let's say that I ask for 2 toppings. Does it make the slightest bit of difference what order I ask for them in? No, absolutely not. They're just going to put them both on top anyway. So every choice of toppings is a combination. Now, here's the list of the 5 that they have available. Marshmallows, Oreos, gummy bears, peanut butter cups, and whipped cream. Now, I chose these 5 to make sure that they all start with a different letter. You'll see why in a second. So suppose you were thinking about this class while you're eating your ice cream. You say, I recognize that each of those choices is a combination. How many different choices did I actually have? Good question. So you take out a piece of paper and you start writing down all the combinations. And this is what you would have come up with. So I wrote them all out with the letters, of course: marshmallow, Oreo, gummy bears, peanut butter cups, and whipped cream. If you write them all out, bearing in mind that the order doesn't matter, it turns out there's 10 different choices we could have made. Okay. And again, if you notice, I do not have a separate listing for OM because the order doesn't matter. Just as long as I pick marshmallows and Oreos, it's the same whether I ask for the Oreos first or the marshmallows. So these are all combinations. And so now that raises an interesting question. How could I calculate this number directly from a formula? Or is there such a formula? And the answer is, of course, there is. So let me show it to you. There is a formula for this. Now, if you notice, I put the permutation down here so you can see them together side by side. Although I think that, let me just do something here. I'd like to make it just a tiny bit neater. So you can really and truly see them side by side. And I wanted you to notice where they're different. There's only one place that they're different. And that's in the denominator. All of a sudden, there's this extra r factorial down there, and that's there because we're stripping out all the cases where we have the same objects, but in a different order. So what this means is that the number of combinations is always smaller than the number of permutations, and in some cases by quite a bit. So now it's a little messier to calculate, but it's not that bad. We'll do several examples and you'll see how straightforward it really is. Okay, so what I'd like to do is revisit that toppings example and prove that there are in fact 10 combinations that we can create when we pick 2 toppings out of 5. So in this case, again, n would be 5 because we had 5 toppings, and then 2 of them we will choose. So r is 2. And so by plugging them all in, n is 5, r is 2. So I've got 5 in the numerator, 5 factorial. Here I have 5 minus 2 factorial times 2 factorial. I'll simplify that just a little. And then I'll go to my calculator and find each of these. Now, by the way, here's where you have to watch it with the keystrokes. We have division here. So when you divide, we open parentheses. So 3 factorial times 2 factorial close equals. That should do it. I'm going to confirm that in mine. 5 factorial divided by, open parentheses, 3 factorial times 2 factorial, close equals. And yes, you do get 10. Actually, let me make this a little bit bigger. Oh, there you go. Boy, you can see that now. Of course, I can't write on it, but you can see it. So there are 10 ways I can choose my toppings. So once you go ahead and do and type those into your calculator, make sure you can replicate that. Just seeing who's here. All right, so does everyone understand? Are we able to get this yourself? Excellent. So guess what? It's time for another one. So here we go. Now this time you're going to a pizzeria. You've got 3 toppings. You can choose any 3 toppings for $2. It's, let's say it automatically, of course, comes with, let's see. No, let me change this a little. It's already got cheese on it. Let me add something else here. What else could you add there? Oh, peppers. Right. All right. So what I was hoping to do here is have 6. Okay. So let's say the pizza automatically comes with cheese, and then you can add any other 3 of these. I mean, cheese and sauce, tomato sauce, of course. And then you can add any of these 3 for another $2. Okay. So that now it makes sense. Now, again, does the order in which I select my toppings matter? No. That means each one of these is a combination. And so because there are 6 choices, n is 6, and we're being given the opportunity to choose three toppings out of the 6, how many choices do you have? So your challenge now, and let me remind you what this formula looks like. Is to figure it out. All right, so let's see who can get there first. How many choices do you have? In other words, how many combinations can we create when choosing 3 toppings out of 6, where the order doesn't matter? All right, you can pop your answer into the chat room if you want. Oh boy, what's taking so long? Ah, here we go. Beautiful. It is indeed 20. Perfect. So let's see why. All right, so you plug in the numbers and you simplify down here, and then you can calculate each one of these. You can calculate them separately and just do it like this, or you can try to do it directly like I showed you before. You'd have to do 6 factorial divided by, open parentheses, 3 factorial times, again, 3 factorial, close equals. Okay, so, and in fact, this is actually very similar to ones we've already done. Yep, that did the job. All right, so we had 20 choices in that case. Okay, let's see. This one, I'll just show this one to you really quickly. This is the case of poker hands. If you're playing poker, a game of draw poker, you have 52 cards in the deck, and everyone gets 5 cards. And so the order in which you receive your cards doesn't make any difference to the value of your hand. So each hand in a game of poker is actually a combination created from choosing 5 objects from 52. So that means we can use this concept to figure out how many poker hands are possible. And so I've done all the steps for you right here. If you let n be 52 and r be 5, it reduces to 52 factorial over 47 factorial times 5 factorial. And if you go through the same keystrokes, you'll get just about 2.6 million. So in other words, you could have 52 factorial divided by, oops, what did I do? Open parentheses, 47 factorial times 5 factorial, close equals. And sometimes when you do these problems, the numbers can be unbelievably large. So don't be put off by that. That happens with this stuff. Oops, hold on. Yeah, it works. Wow. So now you feel like you can do anything with this stuff. Yes. So just remember the combinations are only for cases where the order does not matter. Permutations of the cases where the order does matter. Okay. And arrangements are just when you're taking the entire collection of objects and just changing their order. You're not choosing anything. Like with the posters, you're taking all 4 of your posters and just rearranging them on the same wall. All right. So now I'm going to show you an interesting paradox, I guess you could think of it as. When you were in high school or even or younger, you may have had a locker assigned to you. And then if you did, you probably had to provide your own combination lock. All right. So you all know what a combination lock is. We know what they look like. The standard ones are this is the one. This is the classic. What happens with this lock? You turn the dial right, left, right. Each time you pick a different number. Now, here's the interesting question. Suppose that your combination is 1, 2, 3. Would the lock open for you if you typed in 3, 2, 1? No. So that means that each of these so-called combinations is actually a permutation, because it is treating one, let's say 137 is different than one, let's say 731. So that means that this lock is actually a permutation lock, okay? Because each so-called combination is actually a permutation, given that the order of the numbers matters. So in other words, they're badly named. They should have been named permutation locks. So whoever invented this thing didn't understand math very well and chose to call it a combination lock, but in fact, they are permutation locks. Wow, is anyone shocked by this? Do you feel like society is just unraveling when you see that things are named badly? Is anyone here outraged? You think you can count on things to be named correctly, and then look what happens.
It's blasphemy.
Yeah, I'm like, I don't know what to do. Who can we complain to about this? But you're in the know now. So if you see somebody using a combination lock, you can walk up to them and say, that really should be called a permutation lock. And they'll be very impressed with your intense knowledge of everything under the sun, because who would know something like this except mathematicians? So anyway, that being the case, now the next section is our introduction to probability theory proper. So I have gathered together a set of videos, which I think you'll like very much, that tie together what we're doing here. The first one actually is an introduction to the probability theory that we'll be doing next week. Not next week. No, not next week, the week after. And then the rest of them are more about combinatorics, and some of them are actually kind of a lot of fun. I mean, they're all, teaching us something important, but there's 1 or 2 that are just, let's just say you won't forget these anytime soon. All right, now here's how this has to work though. It's been my experience that when I show these videos, if I try to show it to you directly from here, there often can be issues with the sound. So I have to send this to you through the chat room so you can watch it on your own screen. And then, because believe it or not, by my recording this video, if I include other videos in this video, theoretically, I can be violating copyright laws. So what I'll do is, while the videos are going, I'll have the screen sharing turned off, so that if anyone is watching this video and you notice a bunch of blanks in there, you can find the links to these videos on Moodle. It's right here. So, if you're like, let's just say you couldn't make it today and you're watching this video and you're like, well, what's going on here? I'm seeing 5 minutes of blank space. That's because I've had to turn off the screen sharing. In fact, I almost got into trouble with YouTube once over this. So I know that this is for real. And so you can watch it at home by just clicking on these links on Moodle. Okay. All right. So this first one is an introduction to probability theory. It's a little intense, but he's trying to make it fun. So we'll look at that first, and then we'll save the more fun ones for last. How about that? Okay. So let's get the serious one out of the way, and then we'll look at some ones that are just a little bit more fun. So we'll start with probability theory.
So I've got my essay.
No. All right, here we go. So I'll put it in the chat room. And then you should, now, if you have a problem, seeing it, just let me know, but you should be okay. Watch it on your side of the screen. I won't be able to show it to you here. So, all right, check it out.
And I've been working on it for about a week. So now I'm going to show you how I use Grammarly to edit. Okay, so here's. Hi, I'm Rob. Welcome to Math Antics. In this video, we're going to learn about how to do math with things that only sometimes happen. They might be likely or unlikely. We're going to learn about probability. Usually in math, we deal with things that always happen the same way. They're completely certain. Like if you add 1 and 1, you're always going to get 2. If you multiply 2 and 3, you're always going to get 6. There's no uncertainty at all. But in the real world, things aren't always so predictable. Take a coin toss, for example. We can't predict whether it'll be heads or tails. It's unpredictable or random. And that's why some people will flip a coin to help decide which of two things to do. That's why I make every decision in life. Why am I not surprised? Oh, no. Good luck. But even though we don't know what each coin flip is going to be, we do know a few things about it. We know that with a fair coin toss, that heads is just as likely to show up as tails. The probability of an event, like getting heads or getting tails, is a value that tells us how likely that event is to happen. With our coin toss, since each side is just as likely, and there's only 2 sides to a coin, if we flip the coin a lot of times, we should expect that about half the flips will be heads and about half the flips will be tails. That means that the probability of flipping heads is the fraction 1/2, and the probability of flipping tails is also 1/2. Let's look at this in a little more detail on something called a probability line. It's a number line that goes from 0 to 1. A probability of 0 means that an event cannot happen. It's impossible. And a probability of 1 means that an event is definitely going to happen. It's certain. That's why the probability line only goes from 0 to 1. An event can't be less likely than impossible, and it can't be more likely than certain. A probability of 1/2, like with our coin toss, means that an event is just as likely to happen as it is to not happen. A probability less than 1/2 means that an event is unlikely, and a probability greater than 1/2 means that an event is likely. Oh, and in addition to fractions, it's also common to write probabilities as decimals or percentages, since you can easily convert between those three. A probability of 0 is the same as a 0% chance of something happening. A probability of 1/2 is the same as a 50% chance of something happening. And a probability of 1 is the same as a 100% chance of something happening. Now that you know how a coin toss works, let's see an example of an event that is unlikely, using something a little more complicated than a coin. Let's take a look at dice. A standard die has 6 sides numbered 1 through 6. When you roll it, any of those sides is just as likely to come up as the others. That sounds a lot like flipping a coin, doesn't it? Each side of a die is just as likely to come up as the others, and each side of a coin was just as likely to come up as the other. So you might expect that the probability of rolling a 3 is 50%. But remember, with a coin toss, there are only 2 possibilities, heads or tails. With dice, there are 6 possibilities. And that's going to make a difference in its probability. One way to think about it is that it's certain that one of those 6 sides will land facing upwards, which is a probability of 1 or 100%. But since only one side can face upwards for a given roll, we have to divide up that value among all the possibilities. In the case of a coin toss, since there were only 2 possibilities, we had to divide the probability by 2. 1 divided by 2 is 1/2, which is the decimal 0.5 or 50%. But with the die, we need to divide the probability up evenly between 6 possibilities. 1 divided by 6 is 1/6, which is equivalent to 0.167 or 16.7%. That would be right here on our probability line. That means it isn't likely that I would roll a 3, for instance, but it's just as likely as rolling any other number. And since all 6 numbers have the same probability, each number should come up about as often as the others. To see if they do, I'm going to conduct some trials. That's an excellent argument. Allow me to deliberate. Guilty. Actually, when dealing with probability, a trial, which can also be called an experiment, is a process that has a random outcome, like tossing a coin or rolling dice or spinning a spinner. And the outcome of a trial is what happens in that particular trial, like flipping heads or rolling a 3. So I'm going to conduct several trials by rolling a die multiple times and keeping track of how many times I roll each number. Aha! You said that each number was going to come up just as often as the other numbers. But look, there's more 2s than there are 5s. How do you explain that? Well, remember, we're dealing with things that are random. They're unpredictable. We can't know exactly what will happen, just what will happen on average. So now I have to calculate the average? Well, when we say on average, we mean that the more trials you do, the closer you get to the expected probabilities. Keep watching. There. Now that we've done a lot of trials, you can see that our totals are much closer to what you'd expect them to be. I guess you're probably right. That's one of the really important things to keep in mind about probability. If you do just a few trials, the results might not end up very close to what you'd expect. In fact, they could be way off. But if you do more trials, you increase your chances of reaching the expected probabilities. There's another thing I should point out. Remember, the probability of flipping heads is 1/2, and the probability of flipping tails is 1/2. The probability of rolling a 1 is 1/6, and the probability of rolling any other number on the die is 1/6. If you add up the probabilities for the coin flip, you get 2/2, or 1. And if you add up the probabilities for rolling a die, you get 6/6, which is also 1. And that's not just a coincidence. If you add up the probabilities of all possible outcomes of a trial, the total is going to be 1, or 100%, because it is certain that at least one of those possibilities will happen. Let's look at some more examples. For these examples, we'll use a spinner. If we had a spinner with just 6 equally sized sectors, the probabilities would be exactly the same as with dice. So we want a few more sectors. There, that's more like it. Now we have 16 equally sized sectors. So what's the probability of spinning a 12? Well, just like with dice, where we had to split up the 100% between all 6 possibilities, we'll do the same thing now, but we'll split it up between 16 possibilities. So the probability of spinning a 12 is 1/16, or about 6%, which is right here on the probability line. We can see that the probability of spinning a 12 is less likely than the probability of rolling a 3. And that makes sense because there are more possible outcomes with our spinner. But what if we color some of the sectors a different color and we want to know the probability of spinning a certain color? Now we have 5 sectors colored blue and 11 sectors colored yellow. So what's the probability of spinning a blue? Remember how with the coin toss, we ended up with the fraction 1/2, and with the die roll, we got the fraction 1/6. In both cases, we had 1 as the numerator. And that's because we were interested in only one of the possible outcomes, like the probability of flipping heads or the probability of the number 3 being rolled. But in this case, the top number of our fraction will be 5 because any of these 5 sectors will give us the color we want. And the bottom number will still be the total number of possibilities, which is 16, because that's how many total sectors we have. So the probability of spinning a blue is 5/16, or about 31%. That's still considered unlikely, but it's more likely than spinning a specific number. And this method will work for figuring out the probability of any event. You just make a fraction with the numerator as the number of outcomes that satisfy your requirement, and the denominator as the total number of possible outcomes. Let's try the same method to find the probability of spinning a yellow. Our top number should be 11 because there's 11 yellow sectors, and our bottom number should still be 16. So the probability of spinning a yellow is 11/16, or about 69%. Now we finally have a probability that's considered likely. And it makes sense because you can see by looking at our spinner that it's more likely to spin a yellow than a blue. And you'll notice if we add up 5/16 and 11/16, we get 16/16, or a probability of 1. So that's a good sign that we did it right. Let's look at another example. Suppose we have a bag of marbles. There are 3 green marbles, 7 yellow marbles, and 1 white marble. If we mix them all up and pull out a marble at random, what's the probability of it being green? Well, the top number of our probability fraction will be 3 because there's 3 green marbles. So there's 3 outcomes that get us what we want. And the bottom number will be 11 because there's a total of 11 possible marbles that we could pull out. So the probability of pulling out a green marble is 3/11, or 0.27, or 27%. It's right here on the probability line. That means it's unlikely. And that makes sense because you can see that it would be less likely to pull out a green marble than one of the other ones. Let's try this again for calculating the probability of pulling out a yellow marble. This time, the numerator of our fraction will be 7 because there's 7 yellow marbles. The denominator will still be 11 because there's still 11 marbles total. So the probability of pulling out a yellow marble is 7/11, or 0.64, or 64%. Another example of an event that's likely. How about pulling out the white marble? Well, the top number will be 1, since there's only 1 white marble, and the bottom number is still 11. So the probability of pulling out a white marble is 1/11, or 0.09, or 9%. Not very likely. And if we add up these probabilities, we get 11/11, or 100%, just as we expected. All right, so you should have a pretty good handle on basic probability now. You just have to remember to make a fraction with the numerator being the number of outcomes that give you what you want, and the denominator being the total number of possibilities. And we learned about the probability line, and that a probability can't be less than 0 or greater than 1, or 100%. We also learned that the more trials or experiments you conduct, the closer your results will get to the expected probabilities. Of course, the way to get good at it is to practice. So be sure to do a lot of problems on your own. And as always, thanks for watching Mathematics, and I'll see you next time. And I sentence you to 5 years hard labor. Learn more at mathematics.com. Brilliant helps you see math in a new way.
Oops. All right, so that was interesting. Well, that's was a good background for where we're going with this material, but now we can have some fun ones. Now, this next one involves well, actually it involves arrangements, but in an interesting way. They're going to look at a deck of cards and they're going to come to some surprising conclusions. So let's take a look at this one. All right, let's put that in here. All right, let's check this out.
Pick a card, any card. Actually, just pick up all of them and take a look. This standard 52 card deck has been used for centuries. Every day, thousands just like it are shuffled in casinos all over the world, the order rearranged each time. And yet, every time you pick up a well-shuffled deck like this one, you are almost certainly holding an arrangement of cards that has never before existed in all of history. How can this be? The answer lies in how many different arrangements of 52 cards, or any objects, are possible. Now, 52 may not seem like such a high number, but let's start with an even smaller one. Say we have 4 people trying to sit in 4 numbered chairs. How many ways can they be seated? To start off, any of the 4 people can sit in the first chair. Once this choice is made, only 3 people remain standing. After the second person sits down, only 2 people are left as candidates for the third chair. And after the third person is sat down, the last person standing has no choice but to sit in the fourth chair. If we manually write out all the possible arrangements or permutations, it turns out that there are 24 ways that 4 people can be seated into 4 chairs. But when dealing with larger numbers, this can take quite a while. So let's see if there's a quicker way. Going from the beginning again, You can see that each of the 4 initial choices for the first chair leads to 3 more possible choices for the second chair. And each of those choices leads to 2 more for the third chair. So instead of counting each final scenario individually, we can multiply the number of choices for each chair, 4 times 3 times 2 times 1, to achieve the same result of 24. An interesting pattern emerges. We start with the number of objects we're arranging, 4 in this case, and multiply it by consecutively smaller integers until we reach 1. This is an exciting discovery, so exciting that mathematicians have chosen to symbolize this kind of calculation, known as a factorial, with an exclamation mark. As a general rule, the factorial of any positive integer is calculated as the product of that same integer and all smaller integers down to 1. In our simple example, the number of ways 4 people can be arranged into chairs is written as 4 factorial, which equals 24. So let's go back to our deck. Just as there were 4 factorial ways of arranging 4 people, there are 52 factorial ways of arranging 52 cards. Fortunately, we don't have to calculate this by hand. Just enter the function into a calculator and it will show you that the number of possible arrangements is 8.07 times 10 to the 67th power, or roughly 8 followed by 67 zeros. Just how big is this number? Well, if a new permutation of 52 cards were written out every second, starting 13.8 billion years ago, when the Big Bang is thought to have occurred, the writing would still be continuing today and for millions of years to come. In fact, there are more possible ways to arrange this simple deck of cards than there are atoms on Earth. So the next time it's your turn to shuffle, take a moment to remember that you're holding something that may have never before existed and may never exist again.
Well, that was something to think about. Every time you shuffle the deck, you may be creating a new arrangement that has never been seen before in the history of the entire universe. Now, that's pretty impressive. But it just is a testament to how large 52 factorial really is. It's just beyond belief. All right, now, this next one is really more about probability theory. It's an actual event that happened. And the narrator of this story is a very famous statistician named Ronald Fisher. And about 100 years or so ago, where he was teaching at Cambridge, there's a tea party being held. And one of the waiters was apparently walking around pouring tea into the cups. And this one woman stopped him and said, "Don't do that, please, because I prefer to have my tea poured first and then put the milk in second." And the waiter apparently said to her something like, "Well, how can you tell the difference, madam?" And she said, "Well, I can certainly tell the difference." And so Ronald Fisher, being who he is, decided to conduct an experiment to see if this was for real. And so, but what he basically did was he had 8 cups of tea prepared without her knowledge, and half of them had tea first and half of them had milk first. He asked her to taste them all and write down what she thought about each one. So the results led to some very interesting discoveries in statistics. So I won't spoil the surprise by telling you how it turned out. So instead, let's take a look at this.
Together,
We lost.
Oh, it's over there. No wonder. Oh, all right, there it is.
£40 on Nutrisystem. What I really recommend.
We are in Cambridge, England, 1920. The weather could not have been more perfect for high tea on the terrace. We gathered at the table as a friendly group of colleagues. The gathering had been progressing in a lively fashion, and the teacups were being refreshed when Lady Otterline abruptly stopped the server and pointed out with disdain that he had poured milk first and then tea, rather than abiding by a widely known preference for tea first and then milk. Sidelong glances were exchanged by numerous members of our assembled group as they questioned what difference could it possibly make whether milk or tea were poured first in the cup. It made, according to Lady Otterline, all the difference, a difference she could easily taste. It was at this point that I, as a scientist and amateur detective, decided to step in and proposed a little experiment. Safely away from Lady Otterline's line of vision, 8 cups of tea were prepared. 4 cups with tea poured first, and 4 with milk poured first, always in equal proportions. Happily, Lady Otterline sampled each of the 8 cups and provided the crowd with her judgment of tea or milk first. Remarkably, Lady Otterline identified 8 out of 8 correctly. Could such a feat be accomplished by sheer guesswork? Now, as I mentioned, I'm a scientist above all. As such, I left this little party with more than just some favors. Indeed, I took with me much food for thought. Try my experiment yourself. Consider all the possible results. In what order should your cups be presented? How many cups must be correctly identified to conclude that your subject can truly tell the difference? You will undoubtedly come away with a greater understanding of inferential statistics.
So she got the last laugh, that's for sure. They doubted her, didn't they? But she got them all right. Now, we're going to see in chapter 12 how to calculate the actual probability that she could have gotten them all right by pure chance, but I'll tell you, it's very, very small. So Ronald Fisher concluded that while there's still a remote possibility that she was just lucky, it's so unlikely that he concluded that, of course, she does know the difference between the two. So it's kind of like a good look at the way statistics is done. You very rarely have absolute certainty with statistics. You usually have to go by probabilities and likelihoods. So anyway, I thought you'd like that one. Let's see, what else do we have? All right. Oh, here we go. Now this one is more about probability theory. It's about splitting up bananas on a desert island, but it's worth watching because it'll introduce some more important ideas. And then these last two are especially interesting. But let's take a look at the last banana now.
If you only list your vacation.
Oh. All right, check it out.
Vacation home on Airbnb, you might attract someone looking.
You and a fellow castaway are stranded on a desert island, playing dice for the last banana. You've agreed on these rules. You'll roll 2 dice, and if the biggest number is 1, 2, 3, or 4, player 1 wins. If the biggest number is 5 or 6, player 2 wins. Let's try twice more. Here, player 1 wins. And here, it's player 2. So who do you want to be? At first glance, it may seem like player 1 has the advantage, since she'll win if any one of 4 numbers is the highest. But actually, player 2 has an approximately 56% chance of winning each match. One way to see that is to list all the possible combinations you could get by rolling 2 dice. and then count up the ones that each player wins. These are the possibilities for the yellow die. These are the possibilities for the blue die. Each cell in the chart shows a possible combination when you roll both dice. If you roll a 4 and then a 5, we'll mark a player 2 victory in this cell. A 3 and a 1 gives player 1 a victory here. There are 36 possible combinations, each with exactly the same chance of happening. Mathematicians call these equiprobable events. Now we can see why the first glance was wrong. Even though player 1 has 4 winning numbers and player 2 only has 2, the chance of each number being the greatest is not the same. There is only a 1 in 36 chance that 1 will be the highest number, but there's an 11 in 36 chance that 6 will be the highest. So if any of these combinations are rolled, player 1 will win. And if any of these combinations are rolled, player 2 will win. Out of the 36 possible combinations, 16 give the victory to player 1 and 20 give player 2 the win. You could think about it this way too. The only way player 1 can win is if both dice show a 1, 2, 3, or 4. A 5 or 6 would be a win for player 2. The chance of one die showing 1, 2, 3, or 4 is 4 out of 6. The result of each die roll is independent from the other, and you can calculate the joint probability of independent events by multiplying their probabilities. So the chance of getting a 1, 2, 3, or 4 on both dice is 4 out of 6 times 4 out of 6, or 16 out of 36. Because someone has to win, the chance of player 2 winning is 36 out of 36 minus 16 out of 36, or 20 out of 36. Those are the exact same probabilities we got by making our table. But this doesn't mean that player 2 will win, or even that if you played 36 games as player 2, you'd win 20 of them. That's why events like dice rolling are called random. Even though you can calculate the theoretical probability of each outcome, you might not get the expected results if you examine just a few events. But if you repeat those random events many, many, many times, the frequency of a specific outcome, like a player 2 win, will approach its theoretical probability. That value we got by writing down all the possibilities and counting up the ones for each outcome. So if you sat on that desert island playing dice forever, player 2 would eventually win 56% of the games, and player 1 would win 44%. But by then, of course, the banana would be long gone.
All right. Now this one is going to surprise you to no end. All right. It's called the birthday problem. Well, I think it speaks for itself. They're going to introduce some concepts here, which are based on what we've been doing up to this point today. And they're going to surprise you to no end with the results that they will show you, and they will prove it in great detail. And it's the kind of thing you want to try it out on a group. But let me just send this to you, and you'll see how you react to this one, the birthday problem. All right, check it out.
Imagine a group of people. How big do you think the group would have to be before there's more than a 50% chance that 2 people in the group have the same birthday? Assume for the sake of argument that there are no twins, that every birthday is equally likely, and ignore leap years. Take a moment to think about it. The answer may seem surprisingly low. In a group of 23 people, there's a 50.73% chance that that two people will share the same birthday. But with 365 days in a year, how is it possible that you need such a small group to get even odds of a shared birthday? Why is our intuition so wrong? To figure out the answer, let's look at one way a mathematician might calculate the odds of a birthday match. We can use a field of mathematics known as combinatorics, which deals with the likelihoods of different combinations. The first step is to flip the problem. Trying to calculate the odds of a match directly is challenging because there are many ways you could get a birthday match in a group. Instead, it's easier to calculate the odds that everyone's birthday is different. How does that help? Either there's a birthday match in the group or there isn't. So the odds of a match and the odds of no match must add up to 100%. That means we can find the probability of a match by subtracting the probability of no match from 100. To calculate the odds of no match, start small. Calculate the odds that just one pair of people have different birthdays. One day of the year will be person A's birthday, which leaves only 364 possible birthdays for person B. The probability of different birthdays for A and B, or any pair of people, is 364 out of 365, about 0.997, or 99.7%, pretty high. Bring in person C. The probability that she has a unique birthday in this small group is 363 out of 365, because there are two birth dates already accounted for by A and B. D's odds will be 362 out of 365, and so on, all the way down to W's odds of 343 out of 365. Multiply all of those terms together, and you'll get the probability that no one shares a birthday. This works out to 0.4927. So there's a 49.27% chance that no one in the group of 23 people shares a birthday. When we subtract that from 100, we get a 50.73% chance of at least one birthday match, better than even odds. The key to such a high probability of a match in a relatively small group is the surprisingly large number of possible pairs. As a group grows, the number of possible combinations gets bigger much faster. A group of 5 people has 10 possible pairs. Each of the 5 people can be paired with any of the other 4. Half of those combinations are redundant because pairing person A with person B is the same as pairing B with A, so we divide by 2. By the same reasoning, a group of 10 people has 45 pairs, and a group of 23 has 253. The number of pairs grows quadratically, meaning it's proportional to the square of the number of people in the group. Unfortunately, our brains are notoriously bad at intuitively grasping nonlinear functions. So it seems improbable at first that 23 people could produce 253 possible pairs. Once our brains accept that, the birthday problem makes more sense. Every one of those 253 pairs is a chance for a birthday match. For the same reason, in a group of 70 people, there are 2,415 possible pairs, and the probability that 2 people have the same birthday is more than 99.9%. The birthday problem is just one example where math can show that things that seem impossible, like the same person winning the lottery twice, actually aren't unlikely at all. Sometimes coincidences aren't as coincidental as they seem.
Well, that was pretty interesting. How do you like that? It only takes 23 people in a group to make sure that there's a 50% chance that 2 of them have the same birthday. It just doesn't seem possible. Now, whenever I have shown this video to any of my classes in person, I always ask everybody to tell me their birthdays and see if there actually is a match. And of course, my classes typically have at least 25 students in them, so it's a pretty good experiment. And so I can only remember one time when there was no match in the class. Most of the time, there's been a match. And in fact, one time, the first two people that I asked her birthday actually had the same birthday. It was unbelievable. I mean, I wasn't expecting that, but you know, it happens. It's just a lot more common than you might think. And of course, they went through all the details, but you know, it just still seems a bit paradoxical. So that's why I think you'll remember something like this, and you might even kind of show off this knowledge to somebody, because it is something that's very, very surprising. All right, so we got just one more. This one does sort of tie in with what we're doing, but it has a lot more applications than just in the area of combinatorics. But it's also very interesting and very important, something you may have been exposed to or seen it in high school. Let me go get this last one out. Okay, oh, here we go. All right, one more. It's something called oh, now I lost my place. Here it is. Pascal's triangle. It's possible, like I said, you've heard of this before. But if not, I think you'll find this very interesting. All right, let's check this out.
To study the mammals that lived during the age.
This may look like an arranged stack of numbers, but it's actually a mathematical treasure trove. Indian mathematicians called it the staircase of Mount Meru. In Iran, it's the Khayyam Triangle. And in China, it's Yang-Wei's Triangle. To much of the Western world, it's known as Pascal's Triangle, after French mathematician Blaise Pascal, which seems a bit unfair since he was clearly late to the party, but he still had a lot to contribute. So what is it about this that has so intrigued mathematicians the world over? In short, it's full of patterns and secrets. First and foremost, there's the pattern that generates it. Start with 1 and imagine invisible zeros on either side of it. Add them together in pairs and you'll generate the next row. Now do that again and again. Keep going and you'll wind up with something like this. Though really Pascal's triangle goes on infinitely. Now, row corresponds to what's called the coefficients of a binomial expansion of the form x plus y raised to the n, where n is the number of the row, and we start counting from 0. So if you make n equal 2 and expand it, you get x squared plus 2xy plus y squared. The coefficients, or numbers in front of the variables, are the same as the numbers in that row of Pascal's triangle. You'll see the same thing with n equals 3, which expands to this. So the triangle is a quick and easy way to look up all of these coefficients. But there's much more. For example, add up the numbers in each row and you'll get successive powers of 2. Or in a given row, treat each number as part of a decimal expansion. In other words, row 2 is 1 times 1 plus 2 times 10 plus 1 times 100. You get 121, which is 11 squared. And take a look at what happens when you do the same thing to row 6. It adds up to 1,771,561, which is 11 to the 6th, and so on. There are also geometric applications. Look at the diagonals. The first two aren't very interesting. All ones, and then the positive integers, also known as natural numbers. But the numbers in the next diagonal are called the triangular numbers, because if you take that many dots, you can stack them into equilateral triangles. The next diagonal has the tetrahedral numbers, because similarly, you can stack that many spheres into tetrahedra. Or how about this? Shade in all of the odd numbers. It doesn't look like much when the triangle's small, but if you add thousands of rows, you get a fractal known as Sierpinski's triangle. This triangle isn't just a mathematical work of art, it's also quite useful. especially when it comes to probability and calculations in the domain of combinatorics. Say you want to have 5 children and would like to know the probability of having your dream family of 3 girls and 2 boys. In the binomial expansion, that corresponds to girl plus boy to the 5th power. So we look at the row 5, where the first number corresponds to 5 girls and the last corresponds to 5 boys. The third number is what we're looking for, 10 out of the sum of all the possibilities in the row. So 10 over 32, or 31.25%. Or if you're randomly picking a 5-player basketball team out of a group of 12 friends, how many possible groups of 5 are there? In combinatoric terms, this problem would be phrased as 12 choose 5 and could be calculated with this formula. Or you could just look at the 6th element of row 12 on the triangle and get your answer. The patterns in Pascal's triangle are a testament to the elegantly interwoven fabric of mathematics, and it's still revealing fresh secrets to this day. For example, mathematicians recently discovered a way to expand it to these kinds of polynomials. What might we find next? Well, that's up to you.
Okay, so I guess we're done for today. I hope you have a good spring break. Don't accidentally come to class on Monday because we won't be here. So we'll be off for a week, and when we get back the following Monday, we'll pick it up again with chapter 11. And I'll see you then. Unless you have any last minute questions, I'll see you a week from Monday. Okay, you're welcome. See you next time. Thank you. You too.